Okay, so again, I know that it does involve derivatives, but it's actually really easy to understand Fick's first law if you draw it out. So again, first Fick's first law. What is Fick's first law? It's summarized in this equation. So this equation is the diffusion flux. So J is the diffusion flux is equal to negative, and D, this capital D is the diffusion coefficient times the derivative of concentration over, and this is referring to a location. So again, it's only showing one dimension in this case. Okay, let's draw 2 points and keep it simple. Again, we're only referring to one dimension. So here's location 1, and here's location 2. Now, what happens, say you have, this is representing just the linear one dimension of a solution. So say we have a concentration here and equal concentration of solute in this location as well. So what we have here is that, say this is our location, so again, this is distance here, this is our x, and this y-axis will be our concentration. So actually, I think there's different. So our concentrations at both points are pretty similar. So let's say they're equal. So let's just say this is a concentration arbitrary units. This is the concentration. And notice that the concentration at the first point is equal to the concentration at the second point. Now, what does that mean? So remember, this is actually a ratio, right? This part derivative. And whenever you have a derivative, you're taking the slope of something, how angled it is, right? So what's the slope of this line? So here we have the concentrations are equal, right? So the way you get the slope of something is that, let's take the slope, so C2. So like y2 minus y1 is over x2 minus x1. So the slope is actually equal to this. So because these concentrations over here are equal, that means this equals 0. So if the numerator on top is 0, that means the slope is 0. So when the slope is 0, so this equation here, J equals negative D times 0, that means diffusion flux, the amount of molecules that diffuse over an area over time. So just the rate of diffusion over an area. So this will be 0. And that makes sense because you don't really have net diffusion. If there's no real high or low concentration, then the amount of particles and molecules that diffuse this way will be roughly equal to the amount that diffuses that way. So that's why you have 0 net diffusion flux. Now, what if there is a difference? So say at point 1, that x1 we have here, we have all these particles, and at point 2, we have roughly half the particles. So what do we have here? Just looking at arbitrary units over here. So this is the concentration at point 1, and this is the concentration at point 2. Now, what's the slope? And again, these aren't real units. I'm just drawing arbitrary units over here. So what's the slope of this line? I know, very crooked line. I can't draw. Okay, so what's the slope of this? Well, notice, is the slope positive or negative? Like just in arbitrary units we're seeing here, we have a slope of negative 4/5 because you see the concentration is decreasing, and then you do have like that distance between the 2 points right here. So you have an overall negative slope. Now, without any math, which way are the particles up here going to diffuse? So the way they're going to diffuse is this way. But this is reinforced by the equation because that equation, notice that this negative part right here, if this slope is here and it's negative, so we have negative 4/5 times D equals J. So you actually have that double negatives canceling out. And now you have a positive value. So now you have a positive diffusion flux. And this is what happens here. So because you have positive J, that means diffusion will occur in this direction. So that's why you have the negative, because it's a negative slope, and you are seeing diffusion rate from that high to low concentration. So that's why that negative number is also very important. So we saw this, but what happens if the concentration difference is a little lower? Okay, so let's say we have another solute in that solution. So say we have a solute B, and then here we have the concentration of this solute. So here we have that solute, but the difference in concentration between the 2 points isn't as drastic as in our first solute. So what we have here, we have more solute at point 1, but slightly less in point 2. So again, this is our new concentration. So I don't know, let's call it B1, CB2. All right, so what's the difference in concentration? What's the slope of this new line? Well, we notice that it's still negative because you do have less concentration in this point than you do at this point. But let's plug it into the equation. So times 1/5. So with our solute that doesn't have much of a difference, you notice that we do get a positive integer referring that you do have positive flux. You do have movement from this point to this point of that particular solute. But since the concentration difference isn't as big, since that slope isn't as big, that means this overall rate isn't as large as that solute that had a big difference in concentration. So how do we translate that into regular speak? Big difference in concentration, big rate of diffusion flux. Smaller rate of, or small difference in concentration, you still get diffusion flux from point A to point B, but it's at a lower rate because of a lower concentration difference. Now, if there's no difference between point A and point B, then you're going to get no net diffusion flux. There's no real high or low. Therefore, any particles that diffuse, it'll eventually it balance out and equilibrate, so there's no real net diffusion. So again, that's how you summarize it. All right, so what we saw in the exercise, so the diffusion flux units are moles per meter squared over seconds. So moles is a concentration of molecules, and over seconds, that's referring to a rate. And this meter square, so again, when you have a length and you multiply or you square it, that refers to an area. So it's how many molecules are moving over an area per second. So it's the rate at which these molecules are moving over an area per second. So it makes a lot more sense when you look at the units. Now, what happened when the diffusion, or actually the concentration, the difference between two areas was 0? Well, since the concentration is the same at both points, there's no high, there's no low, so overall, there's no real net diffusion from one area to the other. It's already at equilibrium, it's already balanced. So if there's no difference in concentration, the overall movement is going to be 0, right? Now, what happens when we have a big difference in concentration? If you have a big difference in concentration, this numerator gets bigger. Therefore, diffusion flux also gets bigger as well. So that means when you have a big difference in concentration, you have a faster rate of diffusion flux just by having that big difference in concentration. What if it has a very small concentration or a small difference in concentration? So say one side only has a little more of a solute than the other. Well, compared to the previous example where you had a big difference, a small difference is going to have very slow diffusion. It's still going to diffuse, but relatively less. Smaller numerator, smaller overall number. Therefore, a small difference means little or slower diffusion flux compared to a big difference. And again, this is why that drawing example was really helpful when I was trying to break this equation down. So it's actually a really beautiful equation. It summarizes this okay, the bigger the difference, the faster the flux. Yeah, and it's all summarized within this equation. Now again, second law refers to partial derivatives. I can't explain it more, but I'm talking more about Ficks First Law is the part that is in the APS learning objectives. They didn't really talk about the second law.